Okay, using the wired connection, it's working. So people like Diksha, the birthday girl, asked me about what's going to be on the lab practical or lab skills test tomorrow. So there are two pieces. The first part is a short answer part where you will be explaining basic lab procedures. So I've listed here a number of things that you're going to be asked questions about. These are basic things. If you've been paying attention and doing the labs, they should be fairly easy to you. Things like why are uncertainties required? How do you decide what the uncertainty is going to be? How do you decide what parameters do you use for designing your test of your hypothesis? How do you make a graph? You're going to have to actually make a graph, so you'll want to make sure you label the axes appropriately, draw a best fit line, find the slope from that best fit line. Remember, simple things like don't use any of the points that are given to you to find that best fit line. So that's the first part. Then the second part is going to be a practical part where you're going to be given a set of equipment and asked to find something that's reasonably simple. It's not going to be something that's super complex. And then you're going to need to write out how you're going to do it and summarize your results. And so that's going to be done by yourself. So what I'll actually have is I'll have everybody come in here, and then I'll have some equipment set up in other rooms, and I'll take people to those other rooms to do the practical part.
Is this something you study for, or just hopefully know from doing all the labs?
I can't really think of any way to study for it unless you haven't been doing the labs. If you haven't been doing the labs, then go through the lab manual and see what you were supposed to have been doing. That's the way I view it. Okay, any other questions? Okay, Michael.
This is tomorrow?
Yes, it's tomorrow during lab period. The Flip Friday thing, I didn't make a place for you to turn in until this morning. I'm sorry about that. But there is a place now for you to turn in. You can turn it until 23:55, 11:55 p.m. Okay, going on to the lecture stuff. The picture on the left is the one from Putrajaya, Putrajaya, Malaysia. The one down below, I believe, is from Napa Valley. It's from the Napa Valley Ballooning website, at the very least. We want to understand a little bit about how hot air balloons work. Now, we could probably understand everything without me going through, because a lot of people already understand things like the ideal gas law. But let's start with basic things. This is a hot air balloon. You have a gas burner, right? Okay, that's not a good contrasting color. Here's a good contrasting color. You have a gas burner there. It's burning gas, making hot gas instead of cold gas. A nice exothermic reaction. And so you have hot gas that fills up that balloon. How in the world is that going to make the balloon stay up? What?
Heat rises.
Okay, she said heat rises. Now, you will hear people who will say, well, technically, it's not heat that rises, it's hot air that rises, or hot materials that rise. Same idea, though.
The density is lower of that air inside, just going to be at the same amount, so when it goes up, winds us up.
Okay, you heat the air, and what happens to it?
It expands.
It expands.
The density decreases, and that goes up.
Okay, that's going through the sequence the way I explain it. You have hot air. Because it's hot, that means the molecules are moving faster, something we're going to look at today. Because they're moving faster, they spread out. Another thing we're going to be looking at today. And because they spread out, they're less dense. And so we have less dense air that's contained in that balloon, and it's in more dense, cooler air. And we learned that less dense things float up. And so it floats up because it's less dense. And we could use our equation to calculate the buoyant force by saying, okay, if I look at the balloon itself has a downward force. Force of gravity is equal to the mass of the balloon. Now I'm going to take as an approximation that the payload and the balloon itself have no mass. We know that's untrue. But then we can calculate from that what the payload could be. So we're going to have the force of gravity just of the air inside is the density of the hot air. So I put density with the H for hot, times the volume, that gives me the mass, times G. And just to make sure we're clear on what I skipped, the force load is equal to mass of the load times G. So that's going to be where I include the mass of the balloon and the people hanging from it. And then what's the third force that goes on here? The buoyant force. And the buoyant force buoyant, is equal to the density of the air times volume times G. Now that volume is the volume displaced by the balloon. The other volume was the volume of the balloon. So they're the same volumes. So now we can take this and we can say the sum of the forces on the balloon in the y direction, I'll define y as the vertical direction, is equal to my upward force, which was force buoyant, minus the downward forces, force of the load and the force of gravity. And if it's just going to be hanging still in the air, what's the sum of the forces going to be? 0. What if it's moving up at a constant velocity? What are the sum of forces going to be? Still 0. If it's a constant velocity, even though it's rising, it's still a 0 for the net force. So when people are flying these balloons, they try to keep it so the net force is pretty close to 0. You change it just a little bit to start a descent or start a rise, but you don't want to keep the net force, like let's say you're starting your descent. You don't want to keep the net force down or you're going to speed up downward and crash. So you start it downward at a gentle pace and then come in. So if we use our equations, that would be density of the air, volume G, minus density of my hot air, volume G, minus the mass of the load G is equal to 0. We can see the acceleration of gravity isn't even going to matter for this, and I can calculate the mass of the load that this thing can carry. Is equal to the difference in the densities between my air and my hot air. Do I have a sign problem here? Mass load. A. Oh yeah, density of the air is higher than density of hot air. Duh. I was thinking the other way around. So the different in the densities times the volume. So given that you're probably going to have just about the same density of your hot air no matter what you do, what's going to control how much you can lift with a hot air balloon? The volume of the hot air balloon. Now, something else that I didn't point out that is good to think about. What is the pressure of the air at the bottom of the hot air balloon? 1 atmosphere. It's open to the atmosphere, so it's atmospheric pressure. As you go up inside, what's happening to the pressure? It's going to decrease, but by a very small amount because the density of the air is really small. And the pressure inside and out are essentially the same. The pressure on the inside is just enough to keep it inflated. If you had raised it anymore, it would just go out the bottom. So the pressure difference for something like this is basically 0 from the inside to the out, but you have that buoyant force, the buoyancy. Okay, so let's work on understanding these. First, we have the ideal gas law, and we start with Charles' law. I looked up his name. I think his name was Jacques or something like that. His last name was Charles, so this is taken from another textbook that puts an S apostrophe S. I don't know about you guys. When I was in grade school, they taught us you just put an S apostrophe. What'd you guys learn?
They didn't teach us anything.
They didn't teach us. Excellent.
They do either way.
Either way is what you were taught. Anyway, Charles' law is a law that is taken from doing a constant pressure set of experiments. How do you do constant pressure experiments? Well, that's pretty simple. You just have like a half-inflated balloon in the air. And then you change the temperature, so you heat up the balloon. And what Charles found was when he heated up the air, the balloon expanded. The pressure inside, the pressure outside were seeing an atmospheric pressure, but the volume of the balloon increased. Now, how many people here watch TV show Scorpions? Only a couple or maybe one. They had a rather humorous error in an episode last week. They had a room that for fire suppression they were going to pull out all the air. Now you pull out all the air, what happens to the air pressure? It goes down to nothing, right? Well, there was a water bottle that was empty but had its lid on. And as they pull out all the air, if it has its lid on its sealed, what happens to the pressure inside? It fundamentally stays the same. What happens to the pressure outside? Goes to zero. You have higher pressure inside than outside, what's going to happen? It expands. Did you watch the episode, Michaela?
No, I'm too weak.
Oh, no. Well, what happens is that the water bottle gets crushed by the higher pressure inside. Of course, I watch something like that and it slays me, but it makes me laugh. And yeah, I just had to stop watching The Arrow, honestly, because, The Arrow, or what's the other one? The one that has the guy running around. Flash? Yeah. Flash would kill everybody he ever helps. Why would he kill everyone he ever helps? Yeah. He puts incredible accelerations on these people, which means that there's incredible force required, and he would just snap all these people that he helps. It makes it hard to watch. So, if we take Charles' law, that gives us an extrapolation that shows that all materials are going to have zero volume at a specific temperature. And that's where we get our definition, absolute temperature, or absolute zero, initially. Moving on from Charles' law, we have Gay-Lussac's law. That is his last name. It is not adjective in last name. Gay-Lussac, by the way, was also instrumental in Charles' law. Charles' law was not found by Charles alone. In fact, sometimes you'll find it called, Gay-Lussac and Charles' law or something like that. But Gay-Lussac did experiments where he kept the volume constant. How do you keep the volume constant? Well, I actually have a bulb. I didn't bring it out today for experimentation, but I have a bulb that works for this. It's just a nice, I think it's aluminum bulb. It might be iron. And then you can heat up the air inside or cool down the air inside. It has a little valve on it so I can let air in or let air out if I want, or I can keep it trapped. So he was keeping the air trapped and keeping the volume constant, and he heated it up, and he found that the pressure went up. Cooled down, the pressure went down. So that's Gay-Lussac's law. Then we have two more here. Boyle's law. Boyle kept the temperature constant. So basically, now we have a balloon, and we keep it in the air, but we squeeze it. And so, change the volume, what happens to the pressure under that situation? What he found was, if you take the balloon and you squeeze the balloon, the pressure inside goes up. And these are all proportionalities, by the way. It's not like doing crazy, wacky variations. It's linearly proportional, as shown there. And then Avogadro's law. How many people have ever seen Avogadro's law? Really? I had never seen it before. But Avogadro just said, okay, so if we keep the pressure and temperature constant, if I put more atoms in, what's going to happen to the volume? So that's like, okay, so now I have a balloon, and I'm just going to blow up the balloon. So I have the balloon like this, put some air in, what happened? It got bigger. It's a pretty obvious one to most of us, but not necessarily going to be true. This is one more law than we did on Flip Friday. If you combine them all mathematically, and I'm not going to go through and show the math, I'm not even going to redo the work that you did on Flip Friday, you get a combined relationship of pressure times volume is equal to the number of atoms, N, multiplied by K, the Boltzmann constant, and temperature. So K is just the constant proportionality when you put them all together. So that's our ideal gas law. And that Boltzmann's constant is a very precise number. Many people, I know in my case, I first learned this in chemistry because we took chemistry as a junior and we took physics as a senior in high school. And in chemistry class, they show us the equation like this. PV equals nRT. So that was the first one that I learned. The difference in PV equals nKT and PV equals nRT is you change from using the number of molecules, capital N, to the number of moles, a lowercase n. And the definition to relate those two is shown here. The number of molecules is equal to the number of moles times a constant called Avogadro's number. And I'm not going to talk about atomic mass units right now, so I won't worry about talking about that with regards to Avogadro's number. You do have on your Flip Friday, once again, what's the definition of Avogadro's number. The definition is not 6.022 times 10 to the 23rd. It's something that's a physical measurement that allows you to determine it. In a lot of our physics experiments, we use what we call a closed system, a system where molecules can't come in or leave. In that case, the n, whether it's a capital or lowercase, stays constant. That's a big difference between chemistry and physics and thermodynamics. Chemists tend to have open beakers, and physicists say, let's close the box and keep all of the gas contained. If we keep all of the gas contained, then we should have a simple relationship from the ideal gas law that says PV over T is the same from your starting point to your ending point. So in the majority of our physics problems where n is going to be constant, all you really need to do is identify what's the pressure, the temperature, and the volume we started with, what's the pressure, volume, and temperature we ended with, and you can set them equal and find whichever one you didn't know. Now, this equation, the ideal gas law, whether you write it like this or as shown below, is what we call an equation of state. It's an equation that tells us the state of our gas. Now, it's the ideal gas law, so it's telling us the state of the ideal gas. The variables in this equation are called the state variables. So what are my state variables? Just by reading this, what would they be? Go ahead, read them. Now, if we were in chemistry, we'd add one more, but we're not in chemistry. So those are going to be our state variables. The equation of state is relating those state variables. What's important about a state variable? If you know those numbers, you know exactly what the state of your gas is. Now, thermodynamics is statistical physics. We're talking about statistics. Pressure doesn't apply to a single molecule. It applies to a collection of molecules. And so, what are the microscopic variables that we use to describe a gas? I'm not going to write them down, but what are the microscopic variables we use? The what? Okay, well, we talk about the velocity, we talk about the position, and we talk about the mass, right? Those would be microscopic variables that are all being described by these state variables. So in reality, there are two ways that one could approach talking about gases: using the state variables and the power of statistics, or using the variables for each molecule and having billions upon billions upon billions of equations you're trying to solve. Personally, I go with the simple state variables rather than those billions upon billions of equations to try to simultaneously solve. Okay, first of two clicker questions. You may answer now. which condition is necessary for the ideal gas law to apply? I feel bad because I didn't point out the word. It was in purple, but I didn't point it out on the preceding slides. Although this does obviously relate to the Flip Friday. Okay, we had no clear winner here. Go back to what we learned on Flip Friday. On Flip Friday, we said the textbook gives us one condition for an ideal gas. What was that one condition the textbook gives? High temperature. The textbook says high temperature. That for it to act as an ideal gas, it has to have a high temperature. In the Flip Friday, I said, well, there's really two conditions necessary for something to be an ideal gas. Condition number one is it needs to have no interaction if the molecules come close and don't touch. And if they do touch, it needs to have just elastic collisions. And so how do we make sure that our molecules don't interact if they don't touch and just have elastic collisions if they touch? Or what? Sorry, you said something, man. You all did this on Friday. A high temperature. If it has a high temperature, then the amount of kinetic energy lost in the collision will be a small percentage of the total kinetic energy, so it's very close to an elastic collision. And if it has a high temperature, that means it's going to be traveling really fast. So even if they get close and they have some appreciable force, they're close for so long, or so short amount of time, that it makes no difference. So high temperature assures us that condition of essentially elastic collisions if they collide, and non-interactive if they don't. Now the second condition was that they need to have a no volume. That no volume condition is actually, so the chances of them actually colliding is approaching zero. So how could we make it so they have no volume? Can you take a molecule and just say, oh, I'm going to change one of my state values, pressure, volume, temperature, whatever, and make it so I have no volume for the molecule? Almost a rhetorical question. The answer is, when you can verbalize, no. No, I can't do that. So how can I make the volume negligible? Okay, make it dilute. And so that's what the answer was that was given in the slides. It said that in his work, Gay-Lussac found that it had to be a dilute gas for his equations to apply, and going further from that, then for the ideal gas law, it needs to be a dilute gas, a low density gas. It's not the mass per molecule that's important here, it's the number density. Low number of molecules per unit volume. So if you use the ideal gas law, N over V is the number density. So we had high temperature was necessary given in the textbook. High temperature does lend itself to a lower number density if it's going to behave as an ideal gas. And so I think that's why the textbook only said high temperature, because the high temperature, unless you're really compressing, putting it under really high pressure, it's probably going to have both of the requirements for ideal behavior. Now, something that may or may not confuse you. When you blow up something like a balloon, say you have a beach ball for your balloon. When you start with the beach ball, it's flat. The volume inside is very close to zero. And you start blowing, and you can blow it halfway up and take your mouth away, and what happens? Beach ball is not part of your experience? But you guys have graduation still. Aren't beach balls part of graduation? Certainly, was it part of your graduation from high school?
No, we throw food at people.
You throw food? Oh, the tortillas?
Well, ideally.
Tortillas are great at graduation, but not indoors, see? Because you're just feeding the birds after everybody leaves. Anyway, you blow it up halfway. If you take your mouth off, nothing happens. Because what's the pressure inside if you've only filled the beach ball halfway? It's still just atmospheric pressure. It started atmospheric pressure, it's still atmospheric pressure. All you've done is you put more molecules in. But when you get it completely filled, you're going, getting lightheaded because you're cycling so much air through you. And then all of a sudden, and you can't put it in anymore. What happened?
Pressure rose until your lungs can't exceed that pressure.
Okay, you finally got it filled up. Suddenly, the volume can't expand anymore. You put in more molecules now, and it's going to have to raise the pressure because the volume can't expand anymore. And that's going to require you to blow harder, and all of a sudden, whoa, something happened. So that's what this is about when you fill up a car tire, bicycle tire. When you first put in air, you put a lot of air in, and the pressure hardly changes at all because you're just inflating it to make it fill out. But then once it's filled out, then you put in more air, and then the pressure starts to rise. Now we're going to go through an exercise on the kinetic theory of gases. Now, once again, I'm going to preface this instead of post-face this. I'm going through this derivation so you can see a physical connection and understand why there's a connection between kinetic energy and temperature. So, in the end, you're not going to have to reproduce this, but hopefully it gives you a lot more confidence in the physics, more understanding, that's how it works. So we start with, we have gas molecules that are flying around. In this room, we have gas molecules flying around, hitting everything. So a gas molecule hits my face, comes in, bounces off. If it's behaving like an ideal gas, what's the collision going to be like? An elastic collision. So that means that the velocity of the molecule isn't going to change when it bounces off. Well, the speed of the molecule isn't going to change when it bounces off my head, just the direction. And so if it comes in, okay, here's the normal to my forehead. If it comes in like this, it's just going to bounce off symmetrically on the other side. So only its velocity parallel to the normal to the surface will even change. And so that's what's depicted in this picture here. It comes in with the velocity in the x and y directions, x and y components. Only the x component changes. It changes from into the surface of dx to out of the surface of dx. The y component stays the same. Why is this important? Well, when that molecule bounces off my head, it's not quite as noticeable as if I won't throw this at Chad's head, nor have Chad throw it at my head. But it's not quite as noticeable, but it's the same as if this tennis ball hits my head. It hits my head, it bounces. Okay, fine throw. It hits my head. Let's forget it. I can't throw a ball at my head, apparently. It hits my head and bounces off. When it hits my head and bounces off, you know there's going to be a reaction. My head is going to go backward a little bit. If we got all medieval and said, well, let's try it with this, you would definitely know when this hits my head, I can have my head rebound. There's going to be a change in momentum that this has when it bounces off my head, And that change in momentum is going to correspond to change in momentum of my head. In order to affect a change in momentum, I have to have a force. And so that's what's going to be happening when the molecules hit the wall, or when the molecules hit my head. They bounce off my head, they change momentum, my head is required to put a force outward on them to make them change momentum, and that's what I feel as the air pressure. So let's look at a box filled with a lot of molecules. Okay, after this slide, I put that in because it once again defined ideal gases. I have a box here, and I'm going to look at just this side of the box. And I'm going to calculate the average pressure on that side of the box. Now, I'm going to introduce a notation here that's not in your textbook. There are different ways of writing average. Your textbook uses a bar over the top to say average. So that's the average of the speed squared in the textbook's notation. A clearer way to me of writing that is to put it inside greater than, less than. So that means the average speed squared. Why do I say speed squared? Because we're going to be doing that a lot. So I'm going to start with this and say, okay, the pressure on this green wall is going to be equal to the average force per area of molecules bouncing off of it. Does that make sense? We know pressure is force over area. Because I have a whole bunch of individual things hitting it, I have to look at the average to get my pressure. But then, of course, according to Newton's second law, each molecule has a delta P over delta T when it hits. And that's going to be the force. So I would have this. Now I have to make one correction right now before I forget. I said the pressure is the average force per area. And I said, well, force is change in pressure over change in time. Or not change in pressure over change in time, change in momentum over change in time. But I have more than one molecule in that box. And if I want to find the average, I'm going to be doing this on all of my molecules. So I'm going to have to introduce a times n to get the total, right? Take the average of all the molecules, and then times n, the number of molecules that are striking the surface. And that will give me my pressure. So I had to make that change now before I go further and forget about it. Okay, change in momentum divided by change in time. What is momentum? mv. Now, using the pictures here, it comes in with a velocity vx, parallel or normal to the surface. Comes out with a velocity minus vx. So what do you get for the change in momentum? What's the final momentum? Negative mvx. And what's the initial momentum? mvx. And so my change in momentum minus 2mvx. There's a minus sign here because for random reasons that no other textbook I've ever used, they chose to put the side they're looking at on the right side. If they had used the one on the left side, we would have said that it came in with a negative velocity x and left with a positive velocity x, and then I would have had a plus sign. So this sign, the minus sign here, is only meaningful because of the direction we chose. So it's not going to be important to the answer. So I am going to drop it off here and just say the absolute value of the change in momentum is this. Because I don't want to have that minus sign cluttering up my work. What was that? If it made a difference, right? In this, like I said, in this case, I could have simply drawn my picture differently, and I wouldn't have had that minus sign. So it doesn't make a difference. How do you know? You have to look at something like that before you can decide, oh, it doesn't make a difference. You can't just say, oh, I don't think it's going to matter, this problem, and throw it away. And of course, if I was an astute teacher, I would have just used the other side and never brought it up. Okay, so there's my change in momentum. I need to know the change in time. Now, this is probably the trickiest part of the whole derivation. Let's say I'm looking at one molecule. Can you tell me how long that molecule is going to be in contact with the wall? Okay, not very long is an accurate answer, but the actual value of the answer is no. No, I can't tell you, no one can tell you. Right? It's going to depend on many things, and we don't have that kind of information. But what I can tell you is the average time between collisions. For each collision, it has this change in momentum. And I can tell you the time between the collisions. And so that would be an average for the change in momentum per change in time. So all I need to do is find the time it takes for my molecule to move from the side I care about to the other side and back. Which component of velocity do I care about for that time? Only the x component. What's the relationship between distance and velocity? Okay, velocity is distance over time, which means time should be distance over velocity. So the time between collisions is going to be the distance has to go back and forth, not just one time across the box, but two, divided by the speed. So if I put these two things into my equation, I now have my pressure, my average pressure, is equal to N times the average of 2mVx divided by 2L over Vx times area. Now, assuming it's a fixed box and the mass of my molecule, to make life easy, I'm just going to say, let's say all the molecules are identical mass. Right? So this is taking some assumptions along the way or some restrictions. If they're constant, I can bring them outside of the average. And I have this for my equation. Well, you look at it and you say, wait, length times area. I had a box. For a box, length times area is equal to the volume. Once again, waving of hands, it turns out that this is true regardless of the shape I chose. Right here I chose a box, and so for the box it's true that I could replace that with volume. But it turns out no matter what I chose, this would be correct. That's not a V. And the last step is, this is just the x component of the velocity. But I have molecules flying around with x components, y components, and z components because we live in a three-dimensional space. But if I have random orientations, what can you tell me about the x component average, the y component average, and the z component average? They should be the same. Now, I really need to be a little careful. The x component average, the y component average, and the z component average for speed would be 0. But for speed squared, they're not going to be 0. Right? Because the x component average half would be that direction, half that direction. But it turns out if we have a uniform distribution, randomly distributed, that the average in each of my component directions is the same. And what we really care about is the total squared speed the total squared speed average is equal to the x squared average plus the y squared average plus the z squared, z squared average. But if these are all the same, then that's just equal to 3 times the Vx squared average. So that means that Vx squared is 1/3 of the average velocity squared. Or, excuse me, it's really important to get the words in the right order, of the squared velocity average. And so I can plug this pretty much finally now into that, and I have pressure is equal to N over V times M over 3 velocity squared average. Now I said I'm pretty much done. What remains after this is to take this and relate it to the ideal gas law. I started by saying that I have a gas bouncing around a box. I then got a little more restrictive and said, let's make sure that it's all the same mass for each particle and that it's ideal in behavior. That is, that it has elastic collision. So I've already said it's an ideal gas with a constant mass. So if it's an ideal gas, I should have this obey the ideal gas law. Remind your poor deluded teacher, what's the ideal gas law? Okay, PV is equal to NKT, right? So this here, if I were to solve this for PV over N, I would have on the right side, PV over N is equal to KT. On the left side, I would have PV over N, oh, there's no space there. Equals 1/3 M V squared. Now, going to my next slide, combining those two together, I'm going to put the 1/3 out front, maybe. I have this relationship. So now we can see quite clearly how temperature relates to velocity. That is, the average velocity squared, that works, it's 3 kT. So if I want to find the average velocity, what do I do? Okay. You have to say, not so fast, senor. I can't directly find the average velocity from this. I can square root both sides, but if I square root both sides, I have the square root of the average of the squares. That is not the same as just V. So we call this VRMS is equal to the square root of 3 kT. RMS means square root, mean square. You find it by first squaring your values, then finding the average of the squares, then taking the square root. Question? What was that? The M disappeared in mistake. Thank you. Far better to be corrected than to be wrong and then to the next class period say, by the way. Or even worse, be like some crazy sports announcers who just pretend they weren't wrong. Yeah, I don't like that. So I appreciate you asking. So this root mean squared velocity, that's not the average velocity, but it's something that's going to relate to it. And when we look at the Maxwell-Boltzmann distribution, we'll see a relation. Now, coming back to the equation at the top of the screen, we also note that kinetic energy translational is equal to 1/2 mv squared, which means that the average kinetic energy translational is equal to 1/2 m average velocity squared, or average of velocity squared. So I can take this right here, replace that right there, so I would have 1/3. Notice there's a 1/2 there, so I have to multiply the 2 across to get mv squared by itself. 2 average of kinetic energy translational so that means average kinetic energy translational is equal to 3/2 kT. Two important but related but important outcomes. Now we can see through mathematical derivation of principles that you understood that if I know the temperature and if it's an ideal gas, then that temperature is going to tell me the average translational kinetic energy. What does translational kinetic energy mean? Basically the straight line motion instead of rotating about center motion. So translation, I mean, if something's going like this along a road, I'll still call it translational because it's not going in a circle around the center. So that's what we get from the temperature if it's a monatomic ideal gas. Now what if it's not a monatomic ideal gas makes it so it's just average kinetic energy. It's the translational average kinetic energy for any ideal gas. What if it's not an ideal gas? What if it's a solid? What if I'm talking about this thing? I know its temperature. It's not going to have this same relationship between temperature and the average translational kinetic energy, but there is a relationship. It's just that the constant changes. So temperature is always telling you about the average kinetic energy. It's just not always this equation. Alrighty. So here's the calculations on the RMS speed. I've gone through it. I can skip it. Clicker question number 2. Which kind of energy is proportional to the temperature in an ideal gas? Okay. We had 1, 7, 12. The 12s are correct because we only have a minute left. I am not going to have you talk among yourselves, but it was the translational kinetic energy that it was proportional to. And this set of graphs shows us actually the distribution of speeds of an ideal gas. This is called the Maxwell-Boltzmann distribution. You can see the equation up there in the top right. This is the probability of having a speed based on the temperature. And you can see that if the temperature is lower, then the most probable speed is going to be slower. If the temperature is faster, it's going to be a higher most probable speed. And we will have to stop here. By the way, please pray for the people in the library and the friends of Jeanette. Kind of crazy.